When we talk about faster-than-light travel, we're really talking about a single problem. Space is too big. Even the nearest stars are so far away that traveling at conventional speeds would take decades or centuries. Relativity then makes the problem worse by imposing a hard rule. Nothing can move through space faster than light. Every science fiction solution tries to get around that rule without breaking it directly. They don't try to outrun light. They try to change the structure of space-time itself. Stargates, warp drives, and hyperspace all claim to do that. But they do it in very different ways, and physics treats them very differently. A Stargate, stripped of fiction, is a wormhole, not a metaphorical tunnel, a literal distortion of space-time that connects two distant regions directly. Step in one side, step out the other, without crossing the space in between. This idea actually comes from real physics. Einstein's equations allow wormhole solutions. Mathematically, space-time can be shaped into a tunnel. That part is not controversial. The problem is that these tunnels collapse instantly. Gravity wants to pinch them shut. To keep a wormhole open long enough to pass through, something has to push outward against gravity. That something must have negative energy density, a kind of energy that behaves opposite to normal matter. This is where reality starts to resist. Negative energy is not science fiction, but it only exists in tiny, fleeting amounts in quantum effects. We can measure it in laboratory experiments like the Casimir effect, but the amounts are microscopic. There is no known way to scale it up to something meters wide, let alone stable, safe, and reusable. Even worse, keeping a wormhole open would likely require energy densities comparable to planets or stars, concentrated in ways we do not know how to control. This is not about running a powerful reactor, it's about shaping space-time itself. To even say whether this is possible, we would need a working theory of quantum gravity, a framework that unifies general relativity and quantum mechanics. We do not have that theory. So a Stargate sits in an uncomfortable place. It is mathematically allowed, but physically unsupported. It is closer to real physics than most science fiction, but still far beyond anything we can plausibly engineer. Warp drives feel more scientific, but aren't easier. Warp drives feel different because they don't rely on tunnels. They don't punch holes through space-time. They reshape it locally. The most famous example is the Alcubierre warp drive. In 1994, Miguel Alcubierre showed that Einstein's equations allow a space-time geometry where space contracts in front of a ship and expands behind it. The ship itself doesn't move faster than light. Space does. This is real mathematics. The equations check out. That's why warp drives get serious attention in physics papers and popular science articles. They're not invented out of thin air. But again, the problem is what the equations demand. To create that warp bubble, you still need negative energy density. Large amounts of it. The same exotic requirement as wormholes. Early calculations suggested energy requirements greater than the mass energy of the observable universe. Later papers reduced those numbers dramatically by changing assumptions and geometries. Some estimates dropped to the mass of a large asteroid. That sounds encouraging until you remember that we don't know how to produce even a gram of negative energy on demand. And energy isn't the only problem. Warp bubbles appear to be unstable. They generate extreme radiation at their edges. They may trap particles and release them catastrophically when the bubble stops. Some models suggest you couldn't even turn the drive on or off from inside the ship. So warp drives occupy a strange category. They are not forbidden by known equations, but they rely on forms of matter and control that we have no evidence exist at usable scales. They are mathematically consistent, physically speculative, and technologically unreachable with current knowledge. Hyperspace is different. And worse, hyperspace is often grouped with these ideas, but it doesn't belong in the same category. In most science fiction, hyperspace is a separate realm or dimension where distances are shorter. Ships enter it, travel, then exit somewhere else. This idea feels intuitive, but physics has nothing like it. General relativity does not predict hyperspace. Quantum field theory does not predict it. Even speculative theories with extra dimensions, like string theory, do not allow macroscopic travel through them. Those dimensions, if they exist, are microscopic and tightly constrained. There is no known mechanism to enter another dimension, move through it, and re-enter spacetime elsewhere. There is no math describing how navigation would work. There is no theory explaining how matter would survive the transition. Hyperspace isn't difficult physics. It's undefined physics. It's a narrative shortcut, not an extrapolation. When people talk about these technologies, they often focus on power, fusion reactors, antimatter, stellar-scale energy. That's the wrong bottleneck. The real problem is not how much energy we can generate. It's the kind of energy spacetime demands. Normal matter curves spacetime in one direction. These technologies require curvature in the opposite direction. They require negative energy, exotic stress energy configurations, and control over spacetime at quantum scales. Those are not engineering challenges. They are gaps in fundamental understanding. Without a quantum theory of gravity, we cannot even say whether these structures are allowed in the real universe or whether deeper laws prevent them entirely. Some physicists suspect that nature enforces consistency through mechanisms like Hawking's chronology protection, making macroscopic shortcuts impossible. That's not proven, but neither is the opposite. So, what would we actually need? To build any of these technologies, Stargates, warp drives, anything like hyperspace, we would need breakthroughs on the scale of relativity or quantum mechanics themselves. We would need to understand gravity at the quantum level. We would need to discover or engineer exotic forms of energy. We would need to learn how to shape spacetime deliberately and stably. And we would need experimental evidence that the universe allows such structures at all. Right now, we have none of that. The honest conclusion is this. Stargates are the most grounded of the three, but still speculative. Warp drives are mathematically elegant, but physically implausible. Hyperspace is pure fiction. None of them are waiting for better engines or bigger power plants. They are waiting for entirely new physics. That doesn't make studying them pointless. Wormholes and warp metrics help physicists probe the limits of relativity and quantum theory. They are thought experiments that reveal where our understanding breaks. But as technologies, they remain where they started. In stories. Not because we lack ambition, but because we still don't know what spacetime really is.